here we assume that the system is isotropic in 3 directions. So the expectation value of Vx and Vy and Vz squared should be the same. So we just expect it to be 3 times of the result we just derived. Okay. So at this point, we don't know what this lambda is. Okay. But from the very simple assumptions, basically just from statistical independence, we can get this result. And that's quite surprising. And then the next step is that we want to figure out what is this lambda. Okay. So in order to figure out this lambda, we need to have some kind of microscopic input. So the input that we want to make is that suppose we consider nearby the wall, and we just pick a surface nearby our wall that's denoted by S. And then we pick a small time window, and then the distance that the particle can travel is basically Vx times delta t. Okay, so in principle, your particle can move toward the wall, and after it hits the wall, it will just bounce back. Okay, so we all know that the microscopic meaning of pressure is coming from the force that you applied on the surface of your container. So to estimate that force, basically what we want to estimate is the change of momentum within the small time window delta t. So let's try to estimate what is the change of momentum first. So the change of momentum, at least statistically, we know that it's related to this expression. Okay. Much questions. And the distribution function that we want to that we already got, and the density of the particle in our system, and the surface times the size of this or the length of this box perpendicular to the surface, and this is basically the mass. Okay. Wait. Nope, this is not the mass. The mass is the other part. The 2 coming from the fact that it bounced back, and this is just the volume of the particles that will hit the wall within this limit delta t window. And then, of course, we know that the velocity that will be bounced back will be twice of the difference of the velocity will be -2 times this Vx. Okay. So this expression is basically the change of your momentum within this limited delta t time window. And so what we are trying to do is to figure out what is the pressure under this situation. And in order to evaluate the pressure, we want to evaluate the magnitude of the force divided by the area of the system. Yes? Oh yeah, I times the rho, sorry. So it's like the number of particles. Yeah, okay, good. So are there any other questions? Okay, good. So I'll just keep going. So the force, the magnitude of the force is basically the change of momentum within this delta t time. And we can see that here we have Vx squared, and this f of v is just the distribution function. So we know that what we are actually evaluating is the expectation value of Vx squared. And we already derived that that's basically 1/2 lambda. So eventually we have rho S delta t times minus 2m times bx squared divided by delta t and s. And s and delta t can be eliminated, and we will get also I need to take absolute value of this thing. So I will get rho times 2m divided by 2 lambda. Wait, I'm a bit confused. Did I miss anything? Right. This is integration over just half of the system. So I will need to have another 1/2 outside. Okay. So eventually I'll get rho m divided by 2 lambda. Okay, good. That's there's no problem about that. Okay, so once we know this, the expression for pressure, as we already know in the case of ideal gas, we have the ideal gas equation, PV equal to nRT. So input the pressure and combine these two expressions, then we can figure the lambda is just m divided by 2 kBT. Okay. And there's just some simple manipulation of the algebras. It should not be too complicated. So once we know what is lambda, that means that we can write down what is the velocity distribution function of our system. That's basically square root m divided by 2 pi kBT. This is the normalization factor, and exponential minus m divided by 2 kBT times b squared. That's basically the distribution function after we go through this simple analysis. So let's try to recover what we have done. So the first thing is that statistically, we assume some kind of initial condition, and we require it to satisfy some criteria. In this case, it's basically the statistical independence. And then we assume that it is true for all the time, even though we know it cannot be true. So okay. And then we argue the possible form of the distribution function according to 1. Okay, that's what we did, and we got this exponential minus lambda v squared form. Then we determine the unknown coefficient lambda from the microscopic picture. Of pressure and related with ideal gas equation. Okay. So after these steps, we can pin down what lambda is. Basically, lambda is just m divided by 2kBt. And this gives us the full information of the velocity distribution function. Okay, so that's basically the steps that we have went through. So this is to some extent a simple example to demonstrate the idea. So from now on, basically we'll try to switch gear, as I mentioned, to review of thermodynamics, and I will try to elaborate more about the role that entropy played in the framework of thermodynamics. And from there, we'll try to see if we want to generalize this type of line of arguments to a generic system, how to do that. And those ideas will be basically encapsulated in the Boltzmann's postulate that entropy equal to the nature log of the phase space volume. Okay, so at this point, are there any questions? Okay, so if not, I'm going to enter the review of thermodynamics. Okay. So in order to review thermodynamics, we need to first understand what is a thermodynamic system, or basically it is a macroscopic system. Whose behavior is identified by a small and finite and these quantities are basically the thermodynamic properties or thermodynamic variables. Okay. So so usually, as I mentioned several times, it is not obvious that it could be achieved. But what thermodynamics tells us is that for a thermodynamics system, you can describe your system by some quantities that is relatively, small compared with 10 to the power 23 degrees of freedom. For example, you can characterize it by energy, volume, pressure, and just a handful of parameters. So and also these quantities usually are measurables, or they are determined by experiments. Okay. And In a thermodynamic system, you are allowed to do several things. So once you define your system according to some of the thermodynamic variables, you can try to take it and make contact with another thermodynamic system, which is described by another set of thermodynamic variables. So basically, you can just put them together, okay? So once you put them together, initially, maybe you have your system 1. Maybe I'll use system A to describe it. And they are described by a bunch of thermodynamic variables. And you just put it in contact with another system, system B, which is also described by a set of thermodynamic variables. And then when they, once they are put into contact, then you will see something like that. This is A and this is B. And eventually, they will be described by another set of thermodynamic variables. But now they will reach equilibrium, which means that those variables will become constant in time. Okay, that's basically the operation that you are allowed to do in thermodynamics. And so the question that people, or at least we are trying to ask, is that suppose we know the initial conditions like this xi A and xi B. With those initial conditions, what kind of prediction can we make about the final equilibrium configuration? So that's the question that thermodynamics is trying to ask. And in principle, you could find tons of relation, maybe relation 1 related to xi A and xi B. And the final configuration, maybe you can find relation 1 of it, and maybe you can find relation 2 of these systems also. And maybe you have tons of them, maybe m of them. Okay. So in principle, there are a lot of relations between them. So what thermodynamics is trying to do is that thermodynamics try to focus on the key relations such that once you identify some of the independent relations, then you are able to reconstruct all these possible relations for your system when it reaches equilibrium. So thermodynamics basically try to find the 4 relations. Okay, that's basically what thermodynamics is trying to do. So here we kind of say it very quickly, saying that at the end, the system reaches equilibrium. Okay, but we haven't really defined what do we mean by equilibrium. So here I'm trying to have a short discussion about the concept of equilibrium. Okay. So very, vaguely, when we say something is in equilibrium, what we meant is that this thermodynamic variables, in principle, it should be a function of time. But now, when you wait long enough, it will become something that is constant in time. And once that situation happened, we said the system is in equilibrium. So here I'm just going to quote Feynman's description about equilibrium. Basically, when all the fast processes have already occurred, while the slow ones have yet take place. That's the description, according to Feynman, what we mean by equilibrium. So in this description, you'll notice that it is described by fast and slow, and they are all, to some extent not mathematical as accurate description. So we'll try to make it a little bit more accurate what we mean by fast and slow. So to some extent, when two systems reaches equilibrium at the microscopic level, those particles will basically jiggle around, and the time scale for those little particles is actually quite short. Okay, but in our daily life, the time scale that we are thinking about is like seconds or minutes. If within this observable time, we try to measure our quantity, and if that quantity is not changing within the time that we are interested in, then we can say this system reaches equilibrium. Okay, so that's more like a more practical way to understand what is equilibrium. So in this description, you notice that in order to define what is equilibrium, I need to define what do I mean by the observable time. So that's basically a time window tau that I want to describe my system. Okay, for example, when I'm standing here and try to describe my I don't know, for example, this glass table, then to some extent I can say this glass table is in equilibrium because within the observable time, like during this lecture, like maybe several hours, it basically feels like a solid and sounds like a solid. Okay. However, if you try to ask this question whether this material, this piece of glass, is solid or liquid on a time scale that's like, I don't know, billions of years, then you'll notice that this problem is could be very different compared with what I just described, because this piece of glass can deform, or it can be corrupted, or things like that. So under that situation, of course, we cannot say that this glass table is in equilibrium, because the observation time is so long. Obviously, it will change as a function of time. So the important point that I want to mention is that whenever we are talking about equilibrium, we need to first specify the time scale that we care about. And usually, when we talk about equilibrium in the textbook, we are just assuming that this time scale is set to a reasonable one and stop thinking too much about that. But if you want to have a sharp defined concept of equilibrium, you need to specify the observation time of your system. Okay. So I think that's a very quick overview about what is the concept of equilibrium. And we'll take a 20 minutes break and continue our discussion in our next lecture. Okay, see you after 20 minutes. Okay, so I think we will continue our lecture. So I will just summarize some of the good questions I got during the break. So some of you ask what happened about the, when we do these assumptions about our distribution function, what happened about the real space distribution? And the argument that we are using is that we said that the density is uniform. And the idea is quite, we start from a straightforward gas, like when you have a tank of gas, you expect the density to be uniform. So that's where we start with. But you can also think from what we have learned previously if we have a diffusion equation, and we already solved the diffusion equation when there's no external force, and we know that the long time steady state for diffusion equation without external force will be a uniform distribution. So that's another way to think like why we make this assumption about the uniform distribution. Okay, that's one thing. And the other question is about from the historical point of view, we already know statistical mechanics for classical system at some point. Is it really necessary that in order to understand what do we mean by dilute, we need to include some quantum mechanical description to describe the length scale according to the thermal wavelength? And it turns out that if you want to really stick with the classical picture, then one thing you need to be very careful about is that the ideal gas model, to some extent, we assume that the particles are mathematical points. So it's like a point without any volume or things like that. For a point without volume, then it is basically ill-defined to say whether you are in dilute limit or not, because there's no intrinsic length scale to compare with. Okay. However, if you consider a physical system, for example, you might have a ball or something, then there will be an intrinsic length scale that's basically the size of that ball. Okay. So in practice, it corresponds to the case like, for example, if you are trying to study the ideal gas model in a classical sense, then this ball should be the size of your molecular or the size of your atom. Okay. Then the meaning of dilute is that the mean free path of your system, basically this LF, should be large compared with the size of your microscopic components. That's basically this length scale A. So you can imagine a situation when the mean free path is comparable to this length scale A. Basically, you are in a very packed environment. And in this very packed environment, then collision will be a very regular event. You just, after you move one step to the right, you form a collision with several different particles. Then in that case, you cannot assume that you are in the dilute limit where the frequency that you encounter some interaction is really low. Okay. So that's the two things. And also another thing is that when I'm writing, sometimes I write really fast. So something, if I say something that is not clear, please ask me. And another problem is about this 1/2 when we discuss the collision process. One question is about why we, at the very beginning, we only consider the velocity that is positive. And the reason is because we are analyzing the bouncing event toward the right wall. So only the velocity that is positive, there's a chance that you are able to collide to this right wall. So the other half, if you analyze the events at the left end of your container, then you will need to change this expression to be, integrate over dx, but going from -infinite to 0, because in that case, only the negative component can bounce to the left side of your container. Okay, that's one thing. And the second thing is that when I'm trying to evaluate this integral, this should be connected, but there's just no enough space to that. So in this integral, basically we are integrating over Vx squared with the weighted function that's like a Gaussian. But remember, because we only do the integral over half of the Vx, so in order to connect it with our previous result, which is defined by this expression, which is the average of Vx squared, then we need to be careful, because in this definition, the upper and lower bounds of your integral is basically -infinite to +infinite. Because of that, when we try to replace our expression using this Vx squared expectation value, there's an additional 1/2 outside of the parenthesis. Okay, so that's where this 1/2 came from. And also, when I'm writing down the distribution function, actually, what I have in mind is that this v squared is the magnitude of our velocity vector, which should be correspond to Vx squared plus Vy squared and plus Vz squared. And we derive the distribution function for single x component. So in order to get the velocity distribution function for 3 of them, actually I need to have x component and y component and z component of the distribution function forming a product. So that means like the normalization constant should be raised to the power of 3. That's something I missed in my handwriting. So so there should be a 3 there. And also, I think that's what I have in mind. So are there any questions so far? Okay, so if not, I'll continue. So now we have a rough idea that the definition of equilibrium should be accompanied by the observation time. But for pedagogical reason, that usually we don't specify this observation time, assuming that we know what is the equilibrium configuration. Okay, so okay, so now we are going to try to have a picture about what is thermodynamics. So here I'm just trying to mention some of the laws of thermodynamics. There's law. There's law. That's basically the idea of transitivity of equilibrium. Okay, what that means is that if A and C are in equilibrium, and if B and C are in equilibrium, then A and C are in equilibrium. Okay, so that's just the zeroth law of thermodynamics, and the first law of thermodynamics is related to the conservation of energy. And it should include the total energy of your isolated system, also the heat energy in your system. Okay. So basically, what you said is that, okay, and we have the second law also, which is the entropy. At this point, we haven't defined what that is. Always increases. And then the third law is the entropy at t equal to 0 is 0. Okay. So it depends on how thermodynamics is introduced. Some textbook or some course will use those the 3 laws, including the 0th law of thermodynamics, to formulate the whole framework. Okay, but I'm not going to use this way of describing the thermodynamics. Instead, I'm trying to focus on the description of entropy, at least from the thermodynamic point of view, about what do we mean by that. And also, at this moment, I'm not going to focus on the microscopic meaning of entropy, but instead just interpret it as a macroscopic object. Okay. So in order to do that, let me try to continue by first describe how we describe a thermodynamic system. Okay. So the important thing in this case is the idea of extensive variables. So remember, we said that the thermodynamic system can be characterized by a small set of variables, but within those variables, they still have very different properties. For example, the particle number and the volume of your system, and I don't know, the energy, let me put a question mark here, of our system, and the chemical potential and the pressure and the temperature of our systems, they all belong to the thermodynamic variables. However, for those thermodynamic variables that will scale as your system size, we call it the extensive variables. So what I have here at the first row are examples for the extensive variables. Okay, and at the second rows are basically the intensive variables. Basically, what we meant by that is that if we double the system, like make a second copy of our system, those quantities that will not change as you perform this process is called the intensive variables. And if you double your system, for example, you make a copy of your system that's exactly the same, but you just include it into your system as an extension, then let me try to draw a little bit more. Is n, and when you double it, you basically get double the particle number. Then particle number is considered as the extensive variable. Okay. So so it is obvious that, of course, particle number is going to be an extensive variable. And of course, from the figure, we can also notice that because we are making exactly the same copy, the volume will, of course, be an extensive variable. But why do I, put a question mark at the energy? So intuitively, we'll say that, yeah, energy, of course, it doubles when we increase our system size. But let me try to elaborate more about what we mean by this question mark. Okay, so maybe I should not draw the fancy cubic style cube. Let me just draw a 2D projection, which is easier to understand what I'm trying to say. Suppose in this system, you have energy E, and now you try to double your system such that you have energy E at the left-hand side and energy E at the right-hand side. Then intuitively, you'll say, the E total should be just the sum of these two parts, right? However, one thing that's missing is actually the two parts of your copy, they could have some interaction between them, okay? For example, suppose you have some particles, but they have some charge, like, I don't know, the experiment by Millikan, you have some oil droplets and you try to charge them. Okay, and if you have two containers contain those oil droplets, then they will, of course, interact with Coulomb interaction. Okay, then when you try to double your system, then in that situation, you will need to include E Coulomb, because now the system A can interact with its own copy. So in that sense, energy should not be considered as the extensive variable, because now you have some surface contribution from the interacting between these two systems. However, we are going to make a very strong assumption that we are not studying the system with long-range interaction. Like we are saying that we are not studying something like charged oil droplets. So the interaction between those two components should be relatively short range. What do I mean by relatively short range? It means that only the particles nearby the boundary of these two systems can interact. So particles in here will not interact with the particle that's far away from it, okay? So if you have this assumption, then you can estimate what is the additional energy when you double your system. Basically, if the contact surface for this scene is like S, then the additional energy should be some kind of energy density times the contact surface size. Okay. And why this part of the energy can be neglected? Because when the system is really large, this let's call this I don't know, change of energy due to the surface. Compare with the total energy of your system, it should have the related to the surface area divided by the volume, which is the L, in this case, L times S. Okay. But when the thermodynamic limit, or when we consider the system is really huge, this area will kill each other, and L is sent to infinite, then this ratio of the surface energy with respect to the total energy will become almost like 0. So for short-range interaction, it is a very good approximation to say that energy itself is a extensive variable. Okay, so that's the logic behind when we say energy is an extensive variable. Okay, but there are cases that it might not hold. Okay, so now we have a rough understanding about what are the extensive variables, and what we are going to discuss later or next is about what we mean by intensive variables. And usually those intensive variables are formed by differentiation of two extensive variables. Okay, the reason is that if something you are differentiating is scale with your system size in the same way as some variable that you are changing, then this system size dependence will basically eliminate each other. Then the corresponding quantity like chemical potential, pressure, and temperature will not be dependent on your system size, or will not scale as your system size. So that's the meaning of intensive variables. Okay, so okay, so also another thing, maybe I'll just cheat here. Entropy is also an extensive variable. If you want to understand, or you want to ask what is entropy, then at least at this point we need to in the later it will be postulated as the fundamental property of entropy, but here I'll just say it in advance. Okay, so are there any questions so far? Yes? Oh, that's another good question. If you have a dilute system, what does that mean? It means that the density rho is low enough according to our previous definition of dilute system. So when you double your system, you can ask what is the definition of rho? Rho is basically particle number divided by volume, right? And when you scale your system size doubled, what happened is that n will be doubled again and volume will be doubled again. Yes? Oh, different volume and different particle numbers. So you're saying that, oops. Okay, then I think I roughly understand what you're talking about. Rho A and rho B. And then it is defined this way. And the question is, can I say, if I combine my system, is it still a dilute system? Actually, it is a question, but it is not super closely related to the definition of extensive variable. But I'll still try to explain what do we mean by that. So when we say it is dilute, and you want to consider it as a whole, the first question you need to ask is, when you are trying to connect them, for example, turn it into something like this. Okay, and one is A and one is B. the first question you need to ask is that what's the property of this wall? Okay, if this wall is something like, you know, once you combine them, they just disappear. Then the particle A can travel to particle B. Then it is very likely that the final result depends on what is the exact value of your density profile. Okay, for example, you can consider this thing to be super dense. Okay, and this thing might be a little bit dilute at the border, but once you combine them, then the mean free path is lambda 3 is about, I don't know, several size of your particle's radius. Okay, in that case, it is not clear that you can say it is a dilute system. Okay, so you can always go to this kind of weird situation, but the problem is that once you enter that situation, then the advantage of describe it using some thermodynamics or statistical property becomes quite nasty to deal with. So usually we will stay away from this kind of limit, because unless there are some, you know, intriguing question like we really need to understand that, otherwise I don't think we would discuss that in most of the cases. Yeah. Okay, good. So now let me try to remove that and continue our discussion. Okay, so are there any other questions so far? Okay, so if not, let's just continue. So here's another fundamental hypothesis about thermodynamics. That is basically, let me try to write it down. Okay, so that's the fundamental hypothesis of thermodynamics. That is basically a thermodynamic system can be specified by a set of extensive variables. Okay, so this set will use this abstract notation x not x1 and xr. To xr, it means that you can actually have r extensive variables to specify your thermodynamic system. So usually the convention is that x0 is the most important one. Usually we specify it as the energy. But as I just mentioned, that the fact that energy is an extensive variable is based on the assumption that the particles interact in a short range fashion, or the microscopic components interact with each other in a short range fashion. And x1 usually is considered as the number of particle, and x2 is usually considered as the volume, and of course the list can go on. Okay, so it just means that using these extensive variables, we can specify what is our thermodynamic system. Okay, so now I think we know what is a extensive variable, and we also know the fundamental hypothesis. Then the next we are trying to formulate or like describe what is the central problem of thermodynamics. And actually, to some extent, we already discussed that. That is basically what kind of questions we ask when we talk about a thermodynamic system. Is that we start from some our system A. Now we know that according to the fundamental hypothesis, the system A can be described by a set of extensive variables. Basically, it's this xia. And the system B can be described by xib. Okay. Then we ask the fundamental question of thermodynamics is that when they are interact with each other in some way, the easiest way to make them interact is that we just put them together. And then we ask at the long time equilibrium situation, what will be the outcome or how we describe our final system using the new set of extensive variables. So that's basically the fundamental idea, the fundamental or the central problem of thermodynamics. Okay, so now we know what is the central problem of thermodynamics, but the question is, what's the solution of that? Okay, so at this moment, everything is described in a very abstract way, or like some kind of axiomatic way. And it turns out that the solution of this central problem of thermodynamics is postulated to be the function entropy. Basically, what do I mean by the entropy function is a solution? Is that you can define something, that's what we call the entropy. And there's a protocol that once this entropy function somehow is postulated, then you can use that to get the answer for the central problem of thermodynamics. Okay, so that's how entropy is proposed before we know anything about the microscopic world. Okay, so so let me try to write down more about this, the property of this function. That's basically the property of this entropy. Okay, the first thing is that it is a function of the extensive variables. That sounds obvious because we characterize our system using extensive variables. If it is a solution of the central problem of thermodynamics, it must be, a function of these variables, which is extensive. Okay. And the final answer of the central problem of thermodynamics can be figured out when we maximize this entropy function. Okay. And as we mentioned, there are several fundamental properties for this entropy function. The first thing is that entropy is also an extensive quantity. So if I have a system that is the union of A and B, the entropy of it should be considered as the entropy of system A plus the entropy of system B. Okay. And the next property is a little bit not so trivial. Suppose we have a system this is just a let me try to use maybe I should not use time. So let me just try to describe the system initial state. Yeah. Okay, now let's try to use I. So suppose we have our system and its initial state is described by the extensive variables that we just discussed, and there are of them. And suppose there's another state, let's call it the final state of the same system. And this final state can be characterized by the same set of these extensive variables, but now I'll just label them by F. Okay. So the entropy function, since it is a function of these extensive variables, actually has this special property. That's what we call the concave property. Let me just write down the mathematical description of that. As entropy is a concave function of the extensive variables. So what do I mean by the expression here? So entropy should be a function of these extensive variables. So here this xi just means that there are so many components of it. So let me try to be a little bit more specific about what do I mean by that. Okay, because now we have several different kind of extensive variables. It can be the particle number, it can be the energy, and it can also be the volume of our system. So let's just pick one of the component R. For example, you can think of it as the energy of your system. And then for the two different thermodynamic states, one is the xi and the other is xf. And here, if we try to form to some extent some kind of interpolation between these 2 points, and we assume here alpha is something sitting between 0 to 1. Okay, maybe I should move it to somewhere else. Okay, then we'll found that if we try to interpolate the entropy function within these two thermodynamic point between these two parameter point labeled by the thermodynamic variable xr, it will be greater than the interpolation between the value of the entropy evaluated at these two extensive variable point. Okay, so this is the assumption of the entropy function, and let me try to give a more intuitive understanding about what this is. Okay, so entropy at this point, it is a very generic multivariable function. It is very complicated to imagine what it is doing. So let's try to think about a simple function. For example, something like, I don't know, f of x equal to something, but let's just label it by f of x, and the horizontal axis is our variable. Okay, so for this single variable equation, what does it mean if we have this property? Wait, let's call it xa and xb. Okay, so what do we mean by that when we have only one variable? Okay, so let me just try to give some labels here, and let's try to use a very special case as a benchmarking about what does that mean. So this is the simple, straight line that we are familiar with, f of x equal to kx. Okay, so for this particular choice of our function form, f of x equal to kx, we can ask what is the value from the left-hand side of the equation and the value from the right-hand side of the equation. So the geometric meaning of the left-hand side of this equation just means that you pick some point in here that is represented by, when alpha is 0, it corresponds to xa. When alpha is not 0, it corresponds to somewhere in the middle between these two xa and xb point. Okay, and the left-hand side of the equation is just this value. This is the left-hand side. Okay, and at the right-hand side of this equation of this inequality, it is just the extrapolation of the f of xa and f of xb. Okay, so in this interpolation, you'll see that actually the relation is exactly equal with each other in this linear equation. Okay, so what does it mean when it is larger than this interpolation? We can just simply draw two figures, then we'll know what is the greater and what is the smaller situation. Okay. So suppose we consider the red curve. Okay. For the red curve, basically, the left-hand side will sit in somewhere here. Let's try to like the left-hand side of the red curve, because we are evaluating the function value on this red curve, but with the point that's in the middle of this xa and xb. And we can see that it is larger than the right-hand side of the equation, which is just the interpolation between the endpoints of our function. So entropy should be considered as this kind of concave function. That means like entropy looks more like this kind of bending downward type of function as a function of your extensive variable. Okay, and let me try to be a little bit more careful about that, because in this case, I said this red curve is a concave function. And on the opposite side, this green one is called the convex function. Okay, and this definition is defined is used in most of the convention, but in the textbook of polities, the definition is actually reversed. So let me try to be more careful. wait. But that's fine. The mathematical function form is exactly the same. So if you feel like whether convex or concave is really confusing, you can just stick with the mathematics and it is well defined. Okay. So this is one of the very important property of the entropy. So if we start from this relation, let me just try to copy it and move it to somewhere. And we can take differentiation with alpha from both sides and send alpha to 0. Then you will find this interesting relation, or the useful relation. Evaluated at xi. Wait a second. Let me call this dummy index j in order not to confuse it with our index I. Okay. So it is a easy derivation. You just take derivative with respect to alpha for both sides, and once you after you take the derivative, you just send alpha equal to 0. Then you will get this relation, and at this moment we'll just keep it there and use it whenever we need it. Okay. So the next property of the entropy is that it is a monotonic function, a monotonic increasing function of the internal energy. So energy plays a special role in defining the entropy. So I'll just use E to represent X naught. Internal energy, or simply just the energy. Okay, so what does that mean in the mathematical form is that you take a partial derivative of the entropy function with respect to the energy and evaluate it at constant x1 to xr, which is the rest of the extensive variables. It will be something, let me just write it as 1 over t. It is something that's greater than or equal to 0. So at this moment, the reason I try to write it with as 1 over t is because this expression is actually the definition of temperature in thermodynamics. However, at this moment, it is not very clear. The reason is because we just postulate entropy as a function. When I take a derivative of a function, it just gives me some value. It is not clear that this value has some physical connection with our system. But actually, it can be proved and show that this T is actually the temperature that we are familiar with. Okay. So those are the important properties of the function entropy. And basically, we start by saying that what by introduce what is the central problem. And then we said that, we said the postulate is that the solution of the central problem of thermodynamics is actually, you can derive it from the principle that you want to maximize the function entropy with certain constraints. And those constraints will depend on your physical problems. Okay. So I think we'll try to use a simplest example, that is when we have two systems and try to make contact with each other, and they are allowed to exchange energy, and we can use that to we can use the logic of we just derived previously to understand how these two systems reaches equilibrium. But unfortunately, I realized the time is up, so I think I'll just leave that to our next lecture. So to wrap up, the idea is just simple. I try to give you an abstract way of thinking about thermodynamics and point out the most important question is something that we are already familiar with. Try to bring one thing in contact with the other. Then we ask what's the final, final pressure, or final volume, or final thermodynamic variables will be to describe our final system. And in order to get this, to get a solution of that, what you need is actually you need to define a abstract function which is called entropy. And then by maximize this entropy, at this moment you don't know what is the microscopic meaning of it, but you will find the solution to this thermodynamic problem. So that's the formal structure behind thermodynamics, and I'll stop here, and you can try to ask me any question if you have. And if not, have a nice weekend and see you next week.